All right, now this next section is going to be a little bit intense in the sense that there's going to be a lot of theory and a lot of theorems, particularly about the zeros of polynomials. The actual computations will be kind of minor, and especially on the homework problems. But I want to talk about this because this is going to set us up for the next section, which will lead to one of the most beautiful theorems, the fundamental theorem of algebra. So what we're going to do is I'm going to give you about several theorems. You don't necessarily have to memorize them except maybe one, and I'll tell you which one. And then we'll go from there and see some examples. And these are going to be examples related to the homework. So hopefully you've all had some experience with long division. Certainly maybe long division of numbers. Maybe you've seen long division of polynomials, where you divide one polynomial by another and you get a quotient and a remainder. I'm going to do an example. It won't be exactly, you won't really be tested on this per se on an exam or quiz. But let me just formally say there's actually a theorem which says basically you can divide polynomials. It's called the division algorithm for polynomials. And it says if f and g are polynomials where the degree of g is at least 1, then f of x divided by g of x, this rational function, can be written as a polynomial q plus another polynomial r divided by g. For some polynomials r and g, where the degree of r is strictly less than the degree of g. This would also imply that r of x could be the zero polynomial because the degree of the zero polynomial is defined to be negative infinity. So q is called the quotient and r is called the remainder. And I think just another form you can take this equation, multiply everything by g of x, and you get this. So your first polynomial can be written as the quotient times the second polynomial plus the remainder. And just to show how this might work, maybe you've seen an example like this before. If you wanted to take the polynomial x squared minus 5x plus 7, and let's say you wanted to divide that by x minus 3. You can do this long division where you want to first kill this x squared. So you think, okay, x times what is x squared? Well, that would be x, and we put that above the x term. We multiply this, you get x squared minus 3x. And then we subtract this, and the x squares go away, and then we get negative 5x plus 3x, that's minus 2x, bring down to 7. And then do this again. Then you say, all right, now we want to get rid of this minus 2x. What do we have to multiply x by to get minus 2x? Well, that's minus 2. So you multiply minus 2 times x minus 3, you get minus 2x plus 6. And then you subtract 7 minus, these cancel, and 7 minus 6 is 1. Okay, so we can see that in this case, our quotient is going to be what's up here, x minus 2, and our remainder is going to be 1. Now notice that it has to be, in this case the remainder has to be a constant because the degree of the polynomial we're dividing is 1. So r has to be a constant. It has to be degree 0 because that's the only possible degree that's less than 1. So and then we can see, you can check that this would be equal to x squared minus 5x plus 7. This is equal to x minus 3 times x minus 2 plus 1. Okay. All right. Now, okay. So what? Well, this sort of proves the remainder theorem. Okay. So we said before that if c is a real number and c is a zero of a polynomial, then x minus c has to divide the polynomial f of x. And this works both ways. We say if we know certainly if x minus c is a factor of f of x, if you plug in c, then this will be 0, so this will be 0. But it also works the other way. So the remainder theorem says if f of x is a polynomial and c is a real number, then the remainder when f of x is divided by x minus c is f of c. Now why is that? Well, we're basically applied to the division algorithm and let g of x be x minus c. So f of x is going to be equal to q of x, whatever the quotient is, times x minus c plus a remainder. But again, because the degree of this is 1, so the remainder is just is a constant r. Okay, and this is a number. This is not a polynomial. And then if we plug in x equals c, we get q of c times c minus c plus r. Well, this is 0, so this is going to be r, the remainder. Okay. And as a consequence of that, we get the factor theorem, which says that if f is a polynomial and c is a real number, f of c equals 0 if and only if x minus c divides f of x, because if it divides f of x, then the remainder is 0. There is no remainder. The remainder is 0, and the remainder is f of c, so f of c is 0. As a consequence of this, an important consequence is that if f is a polynomial of degree n, then f of x can have at most n real zeros. The reason for that is, let's say if we have a polynomial where the zeros are 2, 3, 4, and 6, then we know that x minus 2 has to be a factor, x minus 3 has to be a factor, x minus 4 is a factor, x minus 6 is a factor, right? And this, right, if we multiply all these together, the highest power of x will be x to the 4th. Okay. So any polynomial that has these four numbers as their zeros, the degree is going to be at least 4, because the polynomial has to be a multiple of this. Okay. Next one is the other theorem we wanted to talk about is the rational zeros theorem. You may have seen before. And this just says a rational zero is just a rational number that if you plug into the polynomial, you get 0. And the way you do this is you can, there's only finitely many possibilities where this can happen. If we have a polynomial written out in standard form, and all the coefficients are integers, that is whole numbers, and a sub 0 and a sub n are the leading term, and the constant terms are not 0, and then we have a fraction, p over q is a 0 of f, only if if that would imply that p divides a0, the constant term, and q has to divide the leading coefficient, a sub n. So, as an example, if we want to find what the zeros are of the rational zeros of x to the 4th plus 3x minus 4, in this case, the leading coefficient is 1. So a sub 4 is 1, and then the constant is negative 4. So if p over q is a rational 0, then p has to be a divisor of negative 4. So the divisors of negative 4 are the same as the divisors of 4. It's plus or minus 1, plus or minus 2, or plus or minus 4. And of course, q has to divide 1, which means q can only be 1 or negative 1. Okay, and then we take all the possible quotients of these numbers. Plus or minus 1 over plus or minus 1 is plus or minus 1. Plus or minus 2 over plus or minus 1 is plus or minus 2. And then this divided by this is plus or minus 4. So we're going to see that in this case, the only possible rational zeros will be these 6 numbers. Now, obviously, they can't all be zeros because there are 6 of them, and then this polynomial only has degree 4. And in fact, if you were to plug each number in, you'll see that only one is a 0. So just because something could be a rational 0 doesn't mean it will be a 0. And in fact, if we look at the next example here, if we take if we want to find the rational zeros of this, we're looking at numbers p over q, where p is a factor of 3 and q is a factor of 2. So these are the possibilities of p and q, and if you take all the possible quotients, you got plus or minus 1, plus or minus 3, plus or minus 1/2. That's this divided by this, and plus or minus 3/2. And if you plug in these 8 numbers into this polynomial, you'll see that none of them are going to be 0. Okay, so that's going to be this. Again, this is kind of helpful if you're trying to find a 0 and polynomial, and you want to say, well, what are the possible rational zeros? This is the way to get the candidates, and then you check them one by one. Now, this does not solve irrational zeros. Okay, this won't. This you'll never find that a 0 like square root of 2 this way, but this only works for rational zeros.